Hi all, welcome to the class. Today we will learn the basics of cloud-based software. So the convergence of powerful multi-core computer hardware and high-speed networking has led to the development of the cloud. So we all know that the cloud is a very large number of remote servers that are offered for rent by companies that own these servers. So you can rent as many servers as you need, run your software on these servers, and make them available to your customers. So your customers can access these servers from their own computers or other network devices such as tablet or a TV. So you may rent a server and install your own software, or you may pay for access to software products that are available on the cloud. So these remote servers are virtual servers and they are implemented in software rather than hardware. Many virtual servers can run simultaneously on each cloud hardware node using virtualization support. Running multiple servers has very little effect on server performance. The hardware is so powerful that it can easily run several virtual servers at the same time. So cloud companies like Amazon and Google provide cloud management software. It makes it easy to acquire and release servers on demand. You can also automatically upgrade the servers that you are running, and the cloud management software provides resilience in the event of a server failure. So you can rent a server for a contracted amount of time or rent and pay for servers on demand. Therefore, if you need resources for only a short time, then you can simply pay for the time that you need. The cloud servers that you rent can be started up and shut down as demand changes. This means that software that runs on the cloud can be scalable, elastic, and resilient. So, scalability, elasticity, and resilience are the fundamental differences between cloud-based systems and those hosted on dedicated servers. So the main characteristics of cloud-based softwares are scalability, elasticity, and resilience. So scalability reflects the ability of your software to cope with increasing number of users. As the load on your software increases, the software automatically adapts to maintain the system performance and response time. So systems can be scaled by adding new servers, or you can migrate to a more powerful server. So if a more powerful server is used, this is called scaling up. If new servers of the same type are added, then this is called scaling out. So if your software is scaled out, copies of your software are created and executed on additional servers. And elasticity is related to scalability, but allows only for scaling down and scaling up. That is, you can monitor the demand on your application and add or remove servers dynamically as the number of users change. This means that you pay for only the servers you need when you need them. And resilience means that you can design your software architecture to tolerate server failures. You can make several copies of your software available concurrently, and if one of these fails, the others continue to provide a service. You can cope up with the failure of a cloud data center also by locating redundant servers in different places. So if you're setting up a new software product company or development project, it is not cost effective to buy server hardware to support software development. Rather, you should use cloud-based servers that are accessed from your development machines. So the benefits are, first of all, cost. So if you are starting up a new company, you can avoid the initial capital cost of the hardware procurement. And there is no startup time. You don't have to wait for hardware to be delivered before you can start work. And next is server choice. If you find that server you are renting are not powerful enough, Then you can upgrade to more powerful systems. You can also add servers for short-term requirements. And the last benefit is distributed development. That is, if you are a distributed development team working from different locations, all the team members have the same development environment and you can all share the information seamlessly. I will explain some fundamental ideas about cloud-based software that you have to consider when making architecture decisions, and also the idea of containers as a lightweight mechanism to deploy software. So all cloud servers are virtual servers. A virtual server runs on an underlying physical computer and it is made up of an operating system plus a set of software packages, and they provide the server functionality required. The general idea is that the virtual server is a standalone system and it can run on any hardware in the cloud. So this run anywhere characteristic is possible because the virtual server has no external dependencies. So an external dependency means you need some software such as database management system that you are not developing yourself. For example, if you are developing in Python, you need a Python compiler, a Python interpreter, various Python libraries, and so on. So when you run software on different computers, you often encounter problems because some of the external software that you rely on is unavailable or is different in some way from the version that you are using. So if you use a virtual server, you avoid these problems. You load all the software that you need, so you are not relying on software being made available by someone else. So virtual machines running on physical server hardware can be used to implement virtual servers. So the details are complex, but you can think of the hypervisor as providing a hardware emulation that simulates the operation of underlying hardware. So the advantage of using a virtual machine to implement virtual servers is that you have exactly the same hardware platform as a physical server. You can therefore run different operating systems on virtual machines that are hosted on the same computer. For example, Linux and Windows can run concurrently on separate virtual machines. So the problem with implementing the virtual servers on top of virtual machines involves loading and starting up a large and complex operating system. The time needed to install the OS and set up the other softwares on the virtual machines is typically between 2 and 5 minutes on public cloud providers such as AWS. So this means that you cannot instantly react to changing demands by starting up and shutting down virtual machines. So in many cases, you don't really need the generality of a virtual machine. So if you're running a cloud-based system with many instances of applications or services, these all use the same operating system. So to cater to this situation, a simpler, lightweight virtualization technology called containers may be used. Using containers dramatically speeds up the process of deploying virtual servers on the cloud. Containers are usually megabytes in size, whereas virtual machines are gigabytes, and containers can be started up and shut down in a few seconds rather than a few minutes required for a virtual machine. Many companies that provide cloud-based software have now switched from virtual machines to containers because containers are faster to load and less demanding of machine resources. So actually containers are an operating system virtualization technology that allows independent servers to share a single operating system. So they are particularly useful for providing isolated application services where each user sees their own version of an application. So in this figure, A graphic design system product uses basic graphics libraries and a photo management system. A container with the graphic support software and the application is created for each user of the software. So to create and use a container, you use client software to create the container and to load software into that container. And you then deploy the container that you have created onto a Linux server. Using fundamental OS features, the container management system ensures that the process executing in the container is completely isolated from all the other processes. So containers are a lightweight mechanism for running applications in the cloud and are particularly effective for running small applications like standalone services. If your application depends on a large shared database that provides continuous service, running this database on a virtual machine is still the best option. So virtual machines and containers can coexist on the same physical system. So applications running in containers can access the database efficiently. And containers were first introduced in the mid-2000s with developments in the Linux OS. Several companies like Google and Amazon developed and used their own version of containers to manage large server clusters. However, containers really became a mainstream technology around 2015. So now we will discuss the Docker model of containers here. So Docker is an open source project provided a standard means of container management. It is fast and easy to use. It is now the most widely used container technology. So Docker is basically a container management system. It allows users to define the software to be included in the container as a Docker image. It also includes a runtime system that can create and manage containers using these Docker images. So Docker images are directories that can be archived, shared, and run on different Docker hosts. Everything that is needed to run a software system like binaries, libraries, system tools, these are all included in the directory. Therefore, the image can act as a standalone file system for the virtual server. Because of the way Docker has implemented its file system, the image includes only the files that are different from standard OS files. It does not include all the other operating system files that are unchanged. And consequently, images are usually compact and therefore faster to load. So these are the elements of the Docker container system. So this is Docker daemon. This is a process that runs on a host server. It is used to set up, start, stop, and monitor containers. It is also used for building and managing local images. Then we have Docker client. So this software is used by developers and system managers to define and control containers. Then there are Docker files. Docker files define runnable applications or images as a series of setup commands, and it also specifies the software to be included in a container. Each container must be defined by an associated Docker file. Then image. A Docker file is interpreted to create a Docker image. It is a set of directories with specified software and data installed in the right place. Images are set up to be runnable Docker applications. Then there will be a Docker Hub. So this is a registry of images that has been created. These may be reused to set up containers or as a starting point for defining new images. So containers are executing images. So an image is loaded into a container and the application defined by the image starts execution. So containers can be moved from server to server without any modification and also replicated across many servers. So you can make changes to a Docker container, but you then must commit these changes to create a new image and then restart the container. So the file system used in Docker images is called a union file system. So I don't go into details of this here, but it is a bit like an incremental backup where you can simply add the changed files to your backup. And backup software allows you to merge them with previous backups to store your whole file system. In a union file system, you start with a base file system with updates that are specific to an image layered on top of the base. Each update is added as a new layer. The file system software integrates the layers so that you have a complete isolated file system. So a Docker image is a base layer, usually taken from the Docker registry with your own software and data added as a layer on top. And each update to the file system is a layer on top of the existing system. To change an application, all you have to do is ship the changes that you have made to its image, often just a small number of files. You don't have to include any files that are unchanged. So when a container is created, image is loaded and all the files in that image are set as read-only. A read-write layer is added by the Docker daemon to manage local container information, and various initialization parameters are set up by the container management system. Then a process is initialized to run the software defined in the image. The Docker includes a mechanism called bridge network that enables containers to communicate with each other. This means you can create systems made up of communicating components, each of which runs in its own container. And you can also quickly deploy a large number of communicating containers to implement a complex distributed system. You use a management system called Kubernetes to manage the set of deployed containers. You don't need to understand the Docker communication mechanisms to understand the principles of containers. So there are links to information on container communications in the uh, references section. So from a cloud software engineering perspective, containers offer four important benefits. They solve the problem of software dependencies. You don't have to worry about the libraries and other software on the application server being different from those on your development server. Instead of shipping your product as standalone software, you can ship a container that includes all of the support software that your product needs. And they provide a mechanism for software portability across different clouds. So Docker containers can run on any system or cloud provider where the Docker daemon is available. And they also provide an efficient mechanism for implementing software services and so support the development of service-oriented architectures. They simplify the adoption of DevOps. This is an approach to software support where the same team is responsible for both developing and supporting operational software. So rather than buy a software product, we can rent it when we need it. So this idea of a service that is rented rather than owned is fundamental to cloud computing. Instead of owning hardware, we can rent the hardware that you need from a cloud provider. If you have a software product, you can use that rendered hardware to deliver the product to your customers. In cloud computing, this has been developed into the idea of everything as a service. For software product developers, there are currently three levels where everything as a service is most relevant. Infrastructure as a service, platform as a service, and software as a service. So infrastructure as a service is a basic service level and it provides different kinds of services like compute service, network service, and storage service. And these services can be used to implement virtual cloud-based servers. And the key benefits are you don't incur the capital cost of buying a hardware. You can easily migrate your software from one server to another server, and you are responsible for installing the software on the server. It also have some pre-configured packages to help with this. And we also have a control panel. You can easily add more servers if you need to as the load on your system increases. Next is platform as a service. This is an intermediate level where you use libraries and frameworks to implement your software. These are provided by the cloud provider. So these provide access to a range of functions like SQL and NoSQL databases. So using platform as a service makes it easy to develop auto-scaling software, and you can also implement your product so that as the load increases, additional compute and storage resources are added automatically. And the next one is software as a service. So your software product runs on the cloud and is accessed by users through a web browser or a mobile app. So we all know and use this type of cloud service. Mail services like Gmail, storage devices like Dropbox, social media services like Twitter, and so on. So if you're running a small or medium-sized product development company, it is not cost-effective to buy server hardware. If you need development and testing servers, you can implement these using infrastructure services. So you can set up a cloud account with a credit card and be up and running within a few minutes. You don't have to raise capital to buy hardware, and it is also easy to respond to changing demands by upscaling and downscaling your system on the cloud. You can also implement your product on the cloud using platform as a service and deliver your product as a software service. So there are now many companies offering public cloud services to businesses, including large, well-known providers like Amazon, Google, and Microsoft. They all use different interfaces and control panels. So an important difference between these IaaS and PaaS is the allocation of system management responsibilities. So this figure shows who has management responsibilities for software as a service, infrastructure as a service, and platform as a service. So if you are using IaaS, you have the responsibility for installing and managing the database, the system security, and application. If you use PaaS, you can devolve responsibility of managing the database and security to the cloud provider. In software as a service, assuming that the software vendor is running the system on a cloud, the software vendor manages the application. Everything else is the cloud provider's responsibility. When clouds were introduced around 2010, there was a clear distinction between IaaS and PaaS. Amazon presented Amazon Web Services as IaaS. Google, on the other hand, presented their cloud platform as a PaaS environment where you could use Google's cloud primitives to create auto-scaling environments and other features. So there is very little real difference between these levels, with all cloud providers supporting some form of platform as a service. So you may also come across the idea of function as a service. It is supported by Amazon's Lambda service. In this relatively recent development, it is possible to implement a cloud service and start this up and shut it down each time it is used. All you need to do is upload the software implementing the service to the cloud provider, and they create the service automatically. When it is accessed, the server running the service is automatically started. So function as a service has two main benefits. First of all, you don't have to manage a server to run your service. The cloud provider takes full responsibility for this. And the second one is you pay for only the time that the function is executed rather than run. This leads to a significant savings for services like recovery services. So function as a service is a developing area. So software as a service. When software products were introduced, they had to be installed on the customer's own computers. Sometimes the buyer of the software had to configure the software to their own operating environment and deal with software updates. So updated software was not always compatible with other software in the company. So it was common for software users to run older versions to avoid these compatibility problems. So this means the software product company sometimes had to maintain several different versions at the same time of the same product. So many software products are still delivered in this way, but now software products are being delivered as a service. If you deliver your software product as a service, you run the software on your service, which you may rent from a cloud provider. So customers don't have to install the software and they access the remote system through a web browser or dedicated mobile app. The payment model for SAS is usually a subscription. Users pay a monthly fee to use the software rather than buy it overnight. Many software providers deliver their software as a cloud service, but also allow users to download a version of the software so that they can work without a network connection. For example, Adobe offers the Lightroom photo management software as both a cloud service and a download that runs on the user's own computer. So this gets around the problem of reduced performance due to slow network connections. So this table shows the benefits of this approach for product providers. So customers benefit from SAS by avoiding large upfront payments for software and always having access to the latest version. However, some disadvantages in this delivery model dissuade many people from using software that is delivered in this way. So the main advantages are customers either pay regular subscription or pay as they use the software. So there will be a regular cash flow. Then updates, all customers receive the updates at the same time and there will be continuous deployment. The flex payment is also very flexible and we can also try before you buy the product. There will be early free or low cost versions available. And you can also easily collect data on how the product is used and so identify the areas of improvement. So these are the advantages and disadvantages. So one of the most significant business benefits of using SAS is that customers do not incur the capital cost of buying servers or software itself. Customers' cash flow is improved with software being a monthly operational cost rather than a significant capital expenditure. And to maintain access to a service-based software product, customers have to continue to pay, even if they rarely use the software. So this contrasts with software that you can buy for a one-off payment. So once you have bought the software, you can keep it as long as you wish without any further payment. So the universal use of mobile devices means that customers want to access software from these devices as well as desktop and laptop. So delivering SAS means that customers can access the software from any platform at any time. And people can use the software from multiple devices without having to install the software in advance. A further benefit of SAS for customers is that they don't have to employ staff to install and update the system. This transfers the problem of ensuring reliable and consistent service to the SAS provider, and this may lead to a loss of local expertise. A lack of expertise may make it more difficult for customers to revert to self-hosted software if they need to do so. And a characteristic of SAS is that updates can be delivered quickly. New features are immediately available to all customers, and many companies now practice continuous deployment where new versions of the software are delivered every day, and customers have no control over when software updates are installed. Other disadvantages of SAS are related to storage and data management issues. These are important to some customers, especially large multinational companies. They are the fundamental reasons some companies remain reluctant to use cloud-based software and prefer to run software on their own servers. So if you are developing a system that does not deal with personal and financial information, SAS is usually the best way to deliver your soft product. Then, where national or international data protection regulations apply, then the choice is more difficult. You must use a cloud provider that stores data in permitted locations. So if this is impractical, then you may have to provide customer installed software so the data are stored on the customer's own servers. So in some ways, developing software as a service is not different from developing software with a browser interface that runs on organizational servers. So in those situations, you can make assumptions about the available network speed and bandwidth, the electric power available, and the users of the system. So if a software product may be designed so that some features are executed locally in the user's browser or mobile app and some on a remote server, local execution reduces the traffic and increases user response speed. So this is useful when users have a slow network connection. So local processing increases the electric power needed to run the system, but this is not when battery-powered mobile devices are used to access the application. So the best way to distribute local and remote processing depends on the type of application and the expected usage of the system. Consequently, it is difficult to give general advice on this topic apart from experiment and be prepared to change. So on all shared system, users have to authenticate themselves to show that they are accredited to use the system. You can set up your own authentication system, but it means users have to remember another set of authentication credentials. If they don't like that, then many systems allow authentication using Google account or Facebook account or LinkedIn credentials. So this is not usually acceptable for businesses that prefer their users to authenticate using their business credentials. So you may need to set up a federated authentication system that delegates authentication to the business where the user lives. So information leakage is another particular risk for cloud-based software. If you have multiple users from multiple organizations, a security risk is that information leaks from one organization to another. This can happen in a number of different ways. So you need to be very careful in designing your security system to avoid it. So there are multi-tenancy. Multi-tenancy means that the system maintains the information from different organizations in a single repository rather than maintaining separate copies of the system and database. So this can lead to more efficient operation. So many cloud-based systems are multi-tenant systems in which all customers are served by a single instance of the system and a multi-tenant database. So business users interact with that with what appears to be a dedicated system for their company. The database is partitioned so that customer companies have their own space and can store and access their own data. So an alternative software as a service implementation is to provide a separate copy of the system and database for each user. These are called multi-instance systems. So that's all about cloud-based software. Thank you.